Hi, my name is Mike Collier, and this will be an introduction to the next generation of battery technology. It is believed that the first battery ever created was sometime around 200 BC, 2 full millennia before Alessandro Volta's first electrochemical cell in 1800. The ancient batteries were found around 1940 in Iraq. A simple copper sheet formed into a cylinder with an iron rod suspended in a clay pot full of vinegar to produce an electrical reaction that was most likely used for electroplating jewelry. This early battery produced about 2 volts. The battery was named the Baghdad battery. Modern lead-acid technology has not changed much. The use of stronger acid and lead has improved voltage characteristics, stability, and reliability and helped form the modern world. Used in everything from cars to flashlights, batteries have helped shape our lives over 200 years. Keeping in mind that primary batteries are a throwaway type like AAA or AA and used to power small electronics. Secondary batteries are a large rechargeable format typically seen in electric vehicles and power standby solutions. The secondary battery market expects exponential growth within the next 5 to 10 years. This growth will be fueled by the automotive and high-tech industry needs for power backup that cannot be achieved with existing lead or standby generator systems. The demands for smaller, lighter, more powerful, and longer life secondary batteries is pushing a whole new frontier of battery development. With molten sodium, carbon nano, graphene, supercapacitors, and other types of exotic battery technology on the fringe of development, a whole new approach to power and power management is closer than just talk. The aim of new battery development is improved power density for smaller and lighter cells, faster recharge time, higher rates of discharge, longer life or increased number of charge cycles, lower environmental impact, and less expensive to produce. The ability to charge a tablet computer or phone in seconds and drive affordable all-electric vehicles for 500 plus miles is coming soon. New technology development time to market has improved, but at present there is limited technology available for real-world manufacturing. The greatest commercialized battery development in the past 4 years was the development of the lithium battery. At approximately 1/4 the weight and nearly half the volume of lead-acid systems, lithium also has a cycle life in the thousands rather than the hundreds as today's lead batteries. Several commercial variants of lithium chemistry are on today's production market. Some of these variants includes the addition of exotic metals to improve energy storage or cycle life. Lithium cobalt oxide and lithium iron phosphate are 2 notable examples. Lithium cobalt oxide has superior power to weight performance, but has had a history of instability when charged incorrectly or damaged. This instability has led to fires or damage to equipment. Lithium cobalt oxide battery cores were utilized in the highly publicized Boeing battery fires. This lightweight, high-power battery system is also popular with electric vehicle manufacturers. Lithium iron phosphate has less energy density than lithium cobalt oxide, but is more tolerant to abuse. Lithium iron phosphate cells are considered to be the safest of the lithium class batteries by several industry developers. This battery chemistry has over 10 years of commercial service and is utilized by at least 10 major manufacturers worldwide. At present, there are several types of lithium battery core systems manufactured today that provide enough improvement over lead-acid systems to begin making significant market inroads to various industries, such as transportation, grid stabilization, communications, power backup, energy storage, and Department of Defense or military. Lithium battery manufacturers produce the battery cells in 3.2 volt nominal units. These cells can be assembled in combinations of series or parallel to boost voltage or amp hour capacity. For example, 4 100 amp hour cells in series would give a 12.8 volt nominal battery pack. The same 4 cells in parallel would give a 400 amp hour pack at 3.2 volts nominal. By optimizing technology available today, a better and more efficient battery is available now. There are many new battery technology iterations under development. Some are quite exotic, but most are either derivations or incrementations of existing battery technologies. Of these, the most promising to emerge is the lithium titanate battery. The main advantages of lithium titanate or LTO cells are: 1. That they can be charged very quickly. In testing, a 35 kilowatt-hour battery pack was charged in 10 minutes. Comparably, a standard lithium iron phosphate battery would require about 3.5 hours. And longer life. Number 2. With up to 25,000 deep cycles. Comparably, a standard lithium iron phosphate battery would last about 2,000 charge cycles. Other advantages include having a higher power density than other nanostructured cells, wider operating temperature range, and greater stability under electrical and mechanical stresses, i.e., the cells cannot catch fire. These advantages are key to why this chemistry will become the next standard battery technology. Considering the pain points of current batteries in terms of market adoption are: 1. The battery life is shorter than the total product life. 2. Sometimes they catch fire. And 3. Products must be engineered to accommodate installation and replacement of the battery. Because an LTO cell will outlive its host product, and it charges quickly, and it is extremely safe, LTO cells will eventually become an inaccessible integrated component in products. Consumers will always have to be mindful of when to recharge battery-powered products, but they will no longer think of it in terms of a rechargeable battery. They will only see it as recharging the product, and no longer differentiate between the battery and the product. Industrial designers will be able to create sleeker products by eliminating the infrastructure, example ports, lids, spring terminals, etc., needed for installing and replacing batteries. New custom battery shapes can be explored to free product design from the standard rectangle. On a commercial scale, government buildings, data centers, solar and wind energy farms, hospitals, etc. will no longer have the high cost of replacing their massive strings of batteries every 4 years. Money also might be saved in lower insurance premiums, and also LTO cells' tolerance for high discharge will enable these entities to purchase and operate smaller battery systems. The successful commercialization and deployment of LTO cells will change the way our world works, lives, and plays.